Hi everyone, I'm Fion, and I'll be sharing about my final year project, Interpretable Fuzzy Transformer-Based Network with applications in portfolio rebalancing. Traditional financial forecasting techniques, such as ARIMA and GR models, have been long used in the field. In this era of big data, machine learning models have gained popularity for their ability to process data with larger scale and higher dimensions, and also for their high prediction accuracy. Such advancement in forecasting techniques allow deep learning models to be applied to various financial applications, such as stock price forecasting and reversal point prediction. Although deep learning models have high prediction accuracy, these models are essentially black boxes, which means their inner logic cannot be comprehended by humans directly. Having an interpretable model is crucial, as users need to understand how a model makes prediction in order to make necessary adjustments and informed decisions. However, most of the existing studies on using deep learning models for financial forecasting have mainly focused on increasing the accuracy of predictions, neglecting the importance of making the models interpretable. To address this research gap, this project proposed the Interpretable Fuzzy Transformer-Based Network Model, IFTN in short, which combines the interpretability of a fuzzy inference system with the forecasting ability of a transformer-based network model. The proposed IFTN model can be utilized to perform portfolio rebalancing, with the objective of penalizing underperforming markets and capitalizing on well-performing markets. A two-component portfolio reallocation strategy is proposed, and the reallocation process is facilitated by reinforcement learning models. The portfolio used in this project consists of two types of stocks, cyclical stocks and dividend stocks. These stocks were selected using fundamental analysis. Let's first look at the cyclical stocks. IFTN was used to predict future stock prices, and the optimized FMACDH was computed to identify potential trend reversal points. As cyclical stocks are volatile and prices of these stocks fluctuate with the economy cycles, portfolio rebalancing was conducted on these stocks. Before performing prediction, data preprocessing and normalization were performed to obtain three types of input features: close prices, delta price changes, and delta of delta price changes. Next, we perform feature selection using the MCES algorithm to remove irrelevant features. Then, this data were used to perform stock price forecasting with the IFTN model. There are 5 layers in IFTN. Referring to the architecture of IFTN, the CRIPS value will pass into the nodes in the input layer. In the fuzzification layer, localized clustering is performed on the inputs using the DIC algorithm, and the obtained fuzzy sets are the nodes in this layer. There are 2 parallel paths in the rule-based inference layer, the rule-based path and the transformer path. With the predictions generated from the transformer path, the rule-based path uses the Hebbian learning rule to compute the firing strength of each rule. These fuzzy rules provide interpretability for IFTN. The transformer model in the transformer path predicts the stock prices for up to 13 days in the future. The output from transformer path is then passed into the consequent layer. Each node in this layer represents a fuzzy set for output, and these nodes are the consequence for the rules in the rule base. Lastly, the membership values from the consequent layer are passed into the output layer, and defuzzification is performed using the weighted center of averaging method to obtain CRIPS values. The IFTN model was able to achieve an average R-squared score of 0.92, outperforming LSTM model by 90.7% on average. We also perform hyperparameter tuning using genetic algorithm to optimize the model. As seen in the results, we were able to improve the performance of the model for most of the models implemented. Python library was used to visualize vocabulary mappings. Through the visualization, we can see how the antecedents and consequence are linked to the rule node. We can also visualize how the winning input cluster are passed into the encoder layer of the transformer model. The activations of nodes from the last encoder layer to the linear decoder are visualized too. With the forecast from the IFTN model, FMACDH was computed by incorporating the forecast into the equation. The FMACDH was further tuned with genetic algorithm to reduce its lagging effect. Through simulated threading, it was observed that the FMACDH indicator outperformed vanilla MACDH in general, in terms of final portfolio values. As cyclical stocks are highly volatile and their performance are influenced by business cycles, portfolio rebalancing needs to be performed to mitigate risk associated with these fluctuations. When a stock is underperforming, assets need to be reallocated by selling the underperforming stocks and reinvesting the assets into well-performing stocks. Portfolio rebalancing was performed using a RL model with DDPG algorithm. The dividend stocks act as the buffer of the portfolio. These stocks generate stable incomes, and these incomes help to provide stability and lower the overall volatility of the portfolio. Besides, dividend stocks are much more stable than cyclical stocks. Therefore, we are not focusing on rebalancing these stocks, but on the reinvestment of the dividends received from these stocks. The proposed two-component portfolio reallocation strategy consists of rebalancing of cyclical stocks and reinvestment of dividends. By combining the two RL models into an ensemble, the proposed portfolio reallocation strategy was performed. Based on the results, it is evident that the proposed strategy outperformed the traditional buy and hold strategy. In conclusion, this project proposed and developed the IFTN model, which has the capability of accurately forecasting stock prices for up to 13 days in the future. Through vocabulary mappings and rule tagging, the inner logic of the model is visualized. Additionally, this project also proposed two-component portfolio reallocation strategy and demonstrated the utilization of IFTN in this strategy. Thank you.